Yeah, so I'll be talking about our recent work, basically developing the perceiver model for autoregressive generative modeling. So what we've been focusing on in the perceiver line of work is developing architectures that apply quite generically, so basically can be used for any kind of data modality. And we see generation as being really an essential part of having a universal interface that can be used for basically any sort of data and any sort of tasks. So one of the things that we've been working on, especially over the past half year, are better ways to use the same principles that we use for perceivers themselves to sort of allow them to apply for generic inputs and for very, very long inputs, but to use this specifically in the context of best practices for generative modeling. And so Perceiver AR basically shows how to readapt those tricks in the context of autoregressive generative modeling, which allow us to basically use all of the things that make transformers really good in this space. So they're generally applicable. They can be used for discrete data of any kinds, which basically allows them to apply to any kind of data, but also to sort of get past the sort of general limitations in sequence length that you have with standard transformers. So just to give you kind of a high level overview of the big impact here, for transformers, the large language models in particular, we usually apply them up to context lengths of about 2048, which is reasonable for language, but for things like audio, for things like video, 2048 only gives you a very, very small window onto the actual data that you're looking at. With Perceiver AR, we're able to use models that have the same sort of expressive capabilities as transformers. So these are models that can be 60 layers deep with no sweat, but we can use them on sequence lengths up to about 100,000. So we're talking about 1 to 2 orders of magnitude in terms of the increase of the sequence length that we can apply them to, which gives us a lot more flexibility on the kind of data we can use them to without making compromises. Yeah, so I guess my background is in a mix of computational neuroscience and computer vision. And so I came to machine learning via this route. So I was basically working on computer vision systems right around the time of when this sort of the mid 2010s, when the transition was really in full force from sort of classical geometric or optimization based views on how we do computer vision and the neural network, the deep learning revolution. And one of the things that really struck me was at that time was how unified and simple neural networks allowed us to think about systems. So they allowed us to think about basically not just a single problem at one time, but about a whole range of problems in one go. And so since then, I've basically been very interested in methods that allow us to have greater generality, specifically because it allows us to spend most of our time thinking about solving high-level problems in artificial intelligence rather than focusing on the specific details of an individual domain. And so what we've been thinking about in the sort of the perceiver line of work is how we can build the tools that make it easier for researchers to focus on these sort of high-level unified statistical problems rather than thinking about the low-level details of a specific domain when they're designing or building their methods. I guess because I'm going to be talking about focusing on generation, a lot of the important sort of changes in my thinking or the refinements in my thinking recently have been about specifically the power of the very, very simple and unified generative models that we already have. So I think the two most exciting families of models that we have recently are autoregressive models and diffusion models, and I think there's a huge space in between them that we haven't really fleshed out. But so I think the things that really have most guided my thinking recently are about works that have focused on using generation, using the sort of these general, very, very expressive tools for generation in sort of settings where we've classically used kind of hand-designed decoders or problem-specific decoders. So one work that I really, really have enjoyed is this Pix2Seq work from Ting Chen is the first author there. It's work that's happened in Jeffrey Hinton's group at Google. But I really like this because it basically looks at object detection and then in follow-up work and a range of other sort of classical computer vision problems framed with the machinery of sequence-to-sequence modeling with autoregressive models. And what's nice about this is that it basically allows us to sidestep a lot of the engineering details that have happened to make object detection work really well, but have limited its impact specifically to that sort of domain. We've worked in a little bit in this area as well, so both in this perceiver AR work, but also in this really nice work that was led by Charlie Nash here at DeepMind called the Transframer, which is about sort of a different take on the same problem. So I really like Charlie's way of thinking about these problems, which is basically that focused on this idea that we already have most of the tools we need to solve tasks, so autoregressive modeling and diffusion modeling more recently. We just haven't been thinking about ways to unify them. So I think in a lot of ways, my thinking has been sort of redirected to this idea that we should just focus on developing those simple tools that we already have, rather than worrying about sort of artificial problems and sort of thinking about these things as being separate things. Think about them as very simple things and solve them in one go. And so that's really sort of where I've been going recently.